Alright, this is Professor Floyd and OEH 5723, homework 3, problem I. So I'm asking you to calculate the terminal settling velocity. I said in centimeters per second in the problem that I posted, but I don't want it in centimeters per second. I want it meters per second. That's how I'm going to show you to solve it, and I will change that post. I'll change the homework set soon. For those of you that might be watching this after 2014, it's going to be in meters per second, so don't worry about that. So here we are. I want you to calculate the terminal settling velocity at 4 different conditions with 4 different particle densities and sizes. So I could have started this off with one that you'd be able to look up and check, but why do something that's simple like that? Let's just do it on the fly, more difficult. So we're going to start with a rigid sphere with a density given as 18.97 grams per centimeters cubed. Okay. And the diameter, the physical diameter is 0.1 microns. Okay, this is also again equal to 0.1 times 10 to the minus 6 meters. Okay, so if we're going to do this calculation, we need to remember that V sub terminal settling velocity terminal settling, is equal to the density of the particle, not the density of the air this time, the density of the particle, multiplied by the diameter of the particle squared, multiplied by the force of gravity, multiplied by the Cunningham correction factor, that divided by 18 nu, which is the viscosity. So Cunningham correction factor, as you may recall, can be estimated for any given size as 1 plus 2.52 times the mean free path divided by the particle diameter. Okay. So the mean free path at 20 degrees C, because that's generally what we're assuming here, is 0.66. Sorry. It's 0.066 micrometers. And our diameter is also in micrometers, so it's 0.1 micrometers. We can save ourselves the scientific notation by keeping them in the same units, because then these units cancel. Because remember, Cunningham correction factor is a unitless correction. So what we'll find is that for a 0.1 micron spherical aerosol, the Cunningham correction factor comes out to, I did this one ahead of time too, because this is kind of a long problem. We've got 4 sets to it, so I didn't want to belabor over it. I get 2.66. Okay, 2.66. Now if I look that up in Heinz aerosol technology, for a 0.1 micron, we find that it's actually 2.928, so 2.93. So this method for calculating the Cunningham correction factor, like I said, is an estimate. It's not exact. For the sake of this course and just getting you familiar with aerosols, this is plenty accurate enough. If you really want to know how to calculate the Cunningham correction factor, then I suggest that you get this book, and I'll show you that equation right there that I've got my middle finger pointing at. That's the equation that you need. So that's equation 320. Alright, you got that? So if you want to do that, then you can feel free to knock yourself out. And if you do, you will get the same value that is in the back of this Heinz book and so many other aerosol books. So we're using this abbreviated version, and my calculations and everything that I've done and what I'll give you on your take-home assignments or your tests is going to be using this simplified version. So 2.66 is our Cunningham correction. So now we can really just start plugging in, and it's not very complicated at this point. But we also, last thing we need to remember is that our units need to cancel. And so this is grams per centimeters cubed, and our density, if we express it in kilograms per cubic meter, is actually going to be kilograms per cubic meter. Basically, you just make it 1,000 times larger, and then it's kilograms per cubic meter. So it's basically 19,000 kilograms per cubic meter. So now we can do 18,970 kilograms per meters cubed multiplied by our diameter, which is 0.1 times 10 to the minus 6 meters, and then that quantity squared. Then our gravity, the force of gravity is 9.8 meters per second squared. And then our Cunningham correction factor, which I just erased, but this is equal to 2.66. Good thing I can remember that. Or I can look on my cheat sheet. 2.66, it's unitless. And then that would be divided by 18 new, but we're plugging values in. So 1.81 times 10 to the minus 5 kilograms per meter second. Okay. So we can look at our units first, and we see that we're going to have square meters and meters. So we've got cubic meters, which will cancel this out. So these units will end up canceling. We have our kilograms that will cancel, and we have seconds and squared seconds. So these seconds will get rid of the square, and we'll be left with meters per second, as we should be. I'll give myself a little bit more room to write it. So if you punch this number out, what you will find is that it should equal 1.52. Times 10 to the minus 5 meters per second. So I'll just verify that real quick, and we see we have 18,970 times 0.1 e to the minus 6 squared times 9.8 times 2.66 divided by 18 divided by 1.81 to the minus 5, and I get 1.52 actually. Yeah, 1.5178. So 1.52 times 10 to the minus 5 meters per second. So that's how we do it, and that's all there is to it. So now we will move on and basically start plugging in for the other aspects of the problem. So we have a different density on the second set. The second question. The second question gives us a density of 2.68 grams per cubic centimeters, which is also equal to 2,680 kilograms per meters cubed. And then on this one, our diameter is 1 micron. So we're working our way up, getting larger and seeing what this effect will be. So our diameter is 1 micron. So 1 times 10 to the minus 6. So all this is the same. Our Cunningham correction factor needs to be calculated again. So C sub Cunningham is equal to 1 plus 2.52 times 0.066. Let's say that's micrometers. And then we've got 1 micrometer here. So those will cancel, and our Cunningham correction comes out to 1.17. Okay. So 1.17 will go in right there. Actually, it'll go in right here, won't it? So I'm going to get rid of our units just to make this a little bit cleaner and easier. So we have 2,680 times 1 micron squared times gravity times 1.17 for Cunningham correction, and then these remain the same. So our output is in meters per second, but it will be a different value, and the new value is 9.43 times 10 to the minus 5. Okay, 9.43 times 10 to the minus 5. So when we think about that, compared to the previous one, we're roughly 10 times higher. It's 9.43 compared to 1.52. So the previous problem, 18.97 grams per cubic centimeter is really dense. So if we have an aerosol that's that dense compared to an aerosol that is 2.68 grams per cubic centimeter, then we're roughly 10 times more dense. Our diameter was bigger by a factor of 10, but because our particle was so small, we had slip in between that mean free path. And so we had to derate our viscosity by the Cunningham correction. So on the whole, we end up getting we end up getting roughly 10 times, 7.5 times greater terminal settling velocity, even though we got larger by a factor of 10. We would think that the velocity would have gone up faster than that, but it doesn't. Right, sorry, that was kind of a meaningless aside. So I'm actually not going to calculate all the rest of these. This video is already 12.5 minutes long, and the rest of it is just an iteration. I'll give you more practicing. I'll give you one hint, though, on the fourth one, where I ask you for, and I tell you that the aerodynamic diameter is 5 microns. The aerodynamic diameter assumes unit density. So that's your density. It's unit density. And nothing else about that one's very tricky. Your answer should come out to 7.75 for part 4. 7.75 times 10 to the minus 4 meters per second. I hope that helps out.